continue study general relativity through Carol's book at around 120 page. In the end, you should come to accept that profound difference between flat and curved space-time, and some of our favorite notions from flat space physics will be seriously multiplied in this more general context. This is not a sign of any flaw in general, but a natural consequence of discarding the things spectrum we learn to take for granted. That's a different role of it. Instruction for the time serve level speaking to allow and the gradual. This notation is not very formal. You shouldn't push it so far. It will be difficult to associate local and although it's possible in some cases. Okay, 3.6. The Riemann curvature. Yeah, this is a final term, I think, for preparation of general relativity gravitational field, what's called Einstein's equation. So, keep on. Stand on the final step in mathematics. Having set up the machinery of covariant derivative and parallel transport, we are at last prepared to discuss curvature proper. The curvature is quantified by the Riemann tensor, which is derived from the connection. The idea behind this measure of curvature is that we know what we mean by flatness of connection. The conventional connection associated with a Euclidean or in Gaussian metric has a number of properties that can be thought of as a different manifestation. This includes the fact that parallel transport around a closed loop leaves the vector unchanged. As covariant derivatives of tensor commute, and the initial parallel geodesics remain parallel. As we shall see, the Riemann tensor arise when we study how any of these properties are allowed in more general context. We have already argued, using the two spheres as an example, the parallel transport of a closed loop in a curved space to sphere will lead to transformation of the vector. The resulting transformation depends on the total curvature enclosed by the loop. It would be more useful to have a local description of the curvature, which it will Riemann tensor is supposed to provide. One conventional way to introduce the Riemann tensor, therefore, is to consider parallel transport around. We are not going to do, but take a more direct route. Even with working through the detail, it's possible to see what form the answer should take. Since space-time looks flat, small region, our loop will be specified by 2. We imagine parallel transporting a vector v mu by first moving the graph. Then along b mu, the backward along a mu and b mu to return to the starting point as shown. We know the action of parallel transport is independent of coordinates, so there should be some tensors tell us how the vector changes when it comes back to starting point. It will be a linear transformation on a vector and therefore involve one up, but it will also depend on two vectors a mu b that define the loop. A mu b mu. Yeah. Figure. An infinitesimal loop defined by two vector a mu and b nu. The tensor should be antisymmetrical in these two indices, since interchange vector corresponds to transversing group in the opposite direction should give the inverse of original answer. This is consistent with the fact transform should vanish if A and B are the same vector. We therefore expected the expression for the change delta V rho experienced by this vector when parallel transposure on the loop should be one of the form R rho sigma mu V sigma A mu B nu. I think this is a vector. I think this is a why this is a vector. I something right. Look at it should be more useful to. So we are not. I want to. I'm sorry to take a less. I return